Hello and welcome to step 8, implementing the MDN RNN, meaning a recurrent neural network with a mixture density network output layer. So you've just seen the recurrent neural network intuition lectures as well as the mixture density network intuition lectures with Kirill, and now back together we're going to implement from scratch the MDN RNN. So just to make sure everybody's on the same page, what we're about to implement here is of course this component of the full world model, which will be the component that will allow the AI to remember better the time-related correlations in the dream environment and not in the real environment. That's the beauty of this model, to predict better and better actions which will maximize the reward inside the environment. Alright, so no worries, you will learn more about this reward system in step 9, reinforcement learning. But before this, indeed, we need to implement this before we move on to the controller that will eventually play the final actions. So, just before we move on to Python, let me show you what you must absolutely look at in one of the essential resources of this course, which is this amazing article on the full world model written by the original authors. And the section that you must have with you when implementing this is of course this one, MDN RNN. And what you must absolutely understand is that this part of the full world model that we're about to implement is the part that models the probability of the next latent vector given the action that was just played, the current latent vector, and the current hidden state. And then the very important thing to understand about the MDN, and especially its role in the RNN, is that instead of returning the latent vector z's in a deterministic way, it will return them with a probability distribution, meaning that it will return them stochastically. Therefore, it's just like what we did with the CNNVAE. You know, a classic autoencoder returns the latent vectors in a deterministic way, and we added this variational plugin to return them stochastically. And here we're doing exactly the same. Instead of returning the latent vector deterministically, we're returning it with a probability distribution, which means we're going to sample it from this probability distribution in order to predict the next state. And therefore, what it will allow the full world model to do is to predict basically the future. And this is exactly what it says here. The role of the M model is to predict the future, but you have to understand inside the dream. But clearly it works. It improves significantly the performance. All right, and then don't forget also to check out the appendix, because indeed in the appendix you get more details on, well, not only the variational autoencoder, but also what we're about to implement, which is the mixture density network plus recurrent neural network. So you have more details here. This is the classic RNN, but as the output layer of this classic RNN, we're adding the Gaussian mixture, which therefore will return stochastically the latent vector z's, which represent basically the predictions of the future, because as we can see in the full world model graphics, the latent vector z's is an input of the controller. So basically the controller will take as input the latent vector z's of the variational autoencoders, but also the hidden state h returned by the MDN RNN. And it will take these two inputs and return the final action to play inside the environment. And at the same time, you have to be aware of this retro action loop, meaning that the hidden state is given back into the MDN RNN, because indeed this will help predict better the new latent vector z in a stochastic way according to this probability distribution given in the Gaussian mixture. Alright, so let's implement all this on Python now. We will structure the code so that you can clearly see first the RNN part of the MDN RNN, and then separately the Gaussian mixture part, that is the MDN part of the RNN, in a separate code section. And eventually, just like what we did for the VAE, we will implement a separate section for the training operations. And therefore, the code structure will be as followed, exactly the same as what we did for the VAE. First, we will import the libraries, but they will be the same as for the VAE, NumPy and TensorFlow. Then we'll build the MDN RNN model within a class. Then same, we'll have this exact same code section where we initialize all the parameters and variables of the MDN RNN class. And then same, here it will be exactly the same. We will make a build model method which will create the MDN RNN model architecture itself. And inside we'll have 3 separate code sections, just like here. The first one, which will build the RNN part of the MDN RNN. A second one, which will build the MDN part of the MDN RNN. And a third one, which will implement the training operations. So that you can clearly see the structure of what we're implementing and take, whenever you want, a step back to see the general process. All right, so let's do this. And as you understood, since the structure is going to be pretty similar as what we did here for the VAE, well, what we're going to do to be efficient is take everything from here to the top, or up to here, because I already included the title in this new rnn.py file that I've just created. All right, so I'm going to paste this, and now we're going to replace the right things for our MDN RNN model, which are going to be only here, because indeed we will use the same libraries, NumPy and TensorFlow, to build our MDN RNN model. So nothing to change here, but then here, building the, this time, MDN RNN model within a class. Then of course we will change the name of that class and we will call it MDN RNN. Then comes the first code section where we initialize all the parameters and variables of the, this time, MDN RNN class. All right, all good. I always make sure to try as much as I can to create a framework so that we can, switch from one model to another in order to code efficiently. So in the init method, of course, here we'll have to change the parameters because these parameters correspond to the CN and VAE model. And therefore, I'm going to select everything here up to actually here because we will have these 2 arguments for our MDN RNN class and therefore the future instances of this class. But we will add a new one, which will be HPS and which will correspond to the hyperparameters of the MDN RNN model. So don't worry about them now. It's just that in the whole implementation, there will be a hyperparameters class which will gather in one same object all the hyperparameters of the MDN RNN model. But we will actually see them when we build this huge method to create the MDN RNN model architecture as well as the training operation. So we won't miss them, and actually we will create some object variables, of course, for each of them. So HPS here, the hyperparameters, and now let's change what needs to be changed here in order to make it fit to the MDN RNN model. But just before, I'm going to replace VAE here by MDN RNN. And here we go. Now let's initialize the parameters and variables of the MDN RNN class. So I suggest that the way we do this is by just checking each of these lines of code one by one. So self.zsize equals zsize, that was specific to the VAE, so we'll just remove that. Then the batch size. Are we going to have a batch size here? Same, that was specific to the VAE model. Then the learning rate. Yes, we're going to have a learning rate, but of course this learning rate will be included in the hyperparameters, so we will get the learning rate from this HPS object, and therefore we can just remove this. And then KL tolerance, of course, that was specific to the VAE. Then is training, specific to the VAE as well, and then reuse. Yes, we can keep it. Or we can also choose to not keep it, but in that case, we have to replace self.reuse here by just reuse. And this reuse will be exactly this reuse argument here, set by default equal to false. All right, and then before we build the variable scope, for which we'll change the name, of course, well, we have to create one variable object, which is an obvious one, which will contain all the hyperparameters. Because remember, the HPS here, corresponding to the hyperparameters, is just an argument of the init method, therefore of the MDN RNN object when we create an instance of the MDN RNN class. So we have to, as usual, create an HPS variable object of the MDN RNN class, which will be equal to what will be input in the object when creating an instance of the MDN RNN class. All right, so just as usual. And then here comes the variable scope. So of course here we will replace conv VAE by MDN RNN, and then reuse equals reuse because we're not using a variable object. That's optional. Then if not GPU mode, meaning if we're not using a GPU, then we're going to use instead a CPU, which we specify from the device function by TensorFlow. So all good here. Then we have the logging info, which is just like a print saying that indeed our model is using the CPU. Then here we're going to remove this. We're going to create a new variable which will correspond to the graph, just like what we did for the VAE. And we will create a new graph thanks to TensorFlow the same way by calling TensorFlow first. And then from TensorFlow we call the graph class so that this self.g here, variable belonging to the MDN RNN object, will be the graph for this MDN RNN model. So that's something we already did before. Then now we're going to connect all the hyperparameters of our MDN RNN model to this graph. And the way we're going to do this is with an with again. And we are going to specify that by default, this graph is going to be connected to all the hyperparameters. And how are we going to make that connection right here? Well, we will make it by including inside this graph the build model method, which will create the whole MDN RNN model architecture, including the training operations. But as I told you, we're not going to call this method build graph, but this time build model. And that's just to avoid confusion with what we implemented before for the VAE. And therefore, what we have to include here is just self.build model, taking as input the hyperparameters HPS. And therefore here, besides the self, we have to include, of course, the HPS hyperparameters as an argument of this build model method. Right, so now everything is connected well. We have this huge build model method which will build the whole architecture of the MDN RNN, and it is well included inside this graph object variable G for the MDN RNN. And then same in the else, we're going to do kind of the same thing. We can keep the logging info, which will just specify that this time our model is using the GPU in this else condition. And then of course we will replace this self.buildGraph, which was for the VAE, by exactly what we implemented here for the condition when we're using a CPU. So let's just copy that again and let's replace this self.buildGraph by the connection to the build model method. And now let's just be careful with the indents. We have to do it this way. That's the safe way. All right. And now all good. So perfect. Now the initialization of the parameters and variables is done correctly. And now we can move on to the big part of this implementation where we build the full MDN RNN model, including the training operations. So this is going to be a long code section, which of course we'll divide in a couple of tutorials. This whole implementation is about 100 lines of code. So again, get some good energy. Make sure you understand well the intuition and the theory of the MDN RNN model. And as soon as you're ready, let's tackle this together. Until then, enjoy AI.